What if the universe's first interstellar highway wasn't built by us, but by nature itself? Picture a cosmic shortcut, a tunnel woven into the fabric of space and time, connecting two distant points in an instant. This isn't science fiction. Wormholes, those enigmatic bridges predicted by Einstein's equations, might not just be theoretical curiosities, they could be the universe's original transit system, hidden in plain sight. And today, we're diving into 30 breathtaking theories about how the very first wormhole travel might have unfolded, bending the rules of physics and rewriting our understanding of reality. Think about the sheer audacity of it, a structure so powerful, it defies the limits of speed and distance, defying everything we thought we knew about how the cosmos operates. Wormholes aren't just portals, they're time machines, potential gateways to parallel universes, or even relics from the birth of existence itself. Some scientists believe these cosmic tunnels could have formed in the turbulent aftermath of the Big Bang, threading through the newborn universe like veins in a living organism. Others suggest they might be the work of an advanced civilization so ancient, their fingerprints linger in space-time itself. The possibilities are as vast as they are mind-bending. But here's the real thrill: we're standing on the edge of discovery. With every breakthrough in quantum physics, gravitational wave detection, and theoretical modeling, we get closer to unmasking the universe's best-kept secret. Could wormholes hold the key to faster-than-light travel? Could they explain strange anomalies in deep space, or are they cosmic one-way doors, leading to places beyond our wildest imagination? Buckle up, because we're about to explore 30 electrifying theories, from the cutting edge of astrophysics to the fringes of speculative science, that just might reveal how the universe's first wormhole travelers made their impossible journey. The answers will challenge everything you think you know about reality. Einstein's theory of general relativity didn't just reshape our understanding of gravity, it tore open the door to possibilities that sound like pure fantasy. At the heart of this revolution was a radical idea: wormholes, or as physicists first called them, Einstein-Rosen bridges. Picture space not as an empty stage but as a stretchy fabric, warped and dimpled by massive objects like stars and galaxies. Now imagine pinching that fabric so fiercely that two distant points touch, forming a tunnel, a cosmic cheat code, bypassing the vast emptiness between them. That's the essence of an Einstein-Rosen bridge, a structure where space-time folds back on itself, creating a passage that could, in theory, link opposite ends of the universe. The math behind it is both elegant and haunting. When Einstein and his colleague Nathan Rosen tackled the equations of general relativity, they stumbled upon a solution that described black holes not as dead ends, but as gateways. Their work suggested that the crushing gravity of a black hole might not lead to oblivion. Instead, it could funnel matter through a throat of twisted spacetime, spitting it out somewhere else entirely. But here's the catch: these bridges were unstable. The moment anything tried to cross, the tunnel would snap shut like a cosmic bear trap, crushed by its own gravitational forces. Some physicists argue this instability makes them useless for travel, while others see it as a puzzle waiting to be solved. What makes Einstein-Rosen bridges so captivating isn't just their science, it's their legacy. They were the first rigorous proof that shortcuts through space-time weren't just science fiction. Later theories would build on this foundation, suggesting ways to prop wormholes open with exotic matter or manipulate them with unimaginable energies. But it all started here, with two physicists daring to ask, what if the universe itself provided the ultimate shortcuts? Their work didn't just describe wormholes, it hinted at a cosmos far stranger and more interconnected than anyone had dreamed. The universe at its smallest scale is a seething ocean of chaos, but within that chaos, nature might be quietly building the ultimate network of cosmic shortcuts. The quantum foam hypothesis suggests that spacetime itself isn't smooth and placid. When you zoom in close enough down to the Planck scale, where distances are so tiny they make atoms look like planets. Here, the fabric of reality bubbles and churns like a boiling pot, with tiny wormholes constantly blinking in and out of existence. These microscopic tunnels, forged by the raw energy of quantum fluctuations, could be threading through the universe like invisible spider webs, connecting points in spacetime we never knew were linked. So how does this quantum chaos birth wormholes? Picture the vacuum of space not as empty nothingness, but as a frothing sea of virtual particles, pairs of matter and antimatter, that pop into existence for fleeting moments before annihilating each other. These quantum fluctuations warp spacetime itself, creating minuscule tears that could momentarily stitch together into wormholes. The catch: most of these tunnels would vanish almost instantly, collapsing under their own instability before anything could traverse them. But some theories suggest that under the right conditions, perhaps with a jolt of immense energy or a twist of exotic physics, these fragile structures could be stabilized, stretched, and scaled up into something navigable. The implications are staggering. If spacetime is naturally threaded with these quantum wormholes, even at a subatomic level, it means the universe might already be riddled with hidden passageways. We just haven't found them yet. Scaling them up presents a colossal challenge, though. Imagine trying to inflate a soap bubble the size of a pinhead into a tunnel wide enough for a starship. It would require manipulating forces we barely understand, harnessing energies that dwarf anything our technology can currently produce. Yet if it's possible, the payoff would rewrite the rules of existence. A civilization that mastered quantum foam wormholes wouldn't just travel across space, they'd dance through the very fabric of reality itself. Here's where the science gets even wilder. Some researchers speculate these Planck-scale wormholes might not just be spatial shortcuts, they could also serve as time capsules, preserving information from the universe's earliest moments. If a microscopic wormhole formed during the Big Bang's violent birth pangs, could it have trapped a fragment of that primordial energy, carrying whispers of creation itself? Others propose that these quantum tunnels might explain dark matter's elusive nature, acting as conduits for particles we can't directly observe. The quantum foam isn't just a curiosity, it could be the scaffolding of reality, hiding answers to physics' greatest mysteries. But for all their potential, quantum foam wormholes remain tantalizingly out of reach, detecting something trillions of times smaller than an atom, flickering in and out of existence faster than a thought, pushes our instruments to their limits. Yet every breakthrough in quantum gravity, every new glimpse into the subatomic realm, brings us closer to proving whether these phantom tunnels are real, and whether they hold the key to unlocking the universe's deepest secrets. The quantum foam hypothesis doesn't just offer a theory for wormholes, it suggests the cosmos might be more interconnected than we ever dared imagine. Hold on to your seats, because stabilizing a wormhole doesn't just take advanced engineering. It might require ripping a page straight from the weirdest chapters of quantum physics. The problem: wormholes, as Einstein's equations describe them, snap shut faster than a mousetrap under the crushing weight of their own gravity. But there's a theoretical loophole: negative energy. Not just any exotic matter, but stuff that defies the fundamental rules of the universe as we know it, material with a gravitational repulsion so strong it could prop open a wormhole like a cosmic jack. So what exactly is negative energy? Picture the universe's energy budget like a bank account. Ordinary matter, planets, stars, even your morning coffee, carries positive energy, adding to the balance. But quantum mechanics hints at something stranger: regions where the balance dips below zero. These hypothetical pockets would warp spacetime in reverse, pushing against gravity instead of pulling. In theory, lining a wormhole's throat with this repulsive force could counteract its natural collapse, turning a fleeting tunnel into a stable corridor. The catch: we've never observed negative energy in bulk. It's like trying to build a bridge out of a material that might not even exist. The closest we've come is the Casimir effect, a eerie quantum phenomenon where two metal plates, placed impossibly close in a vacuum, experience a slight attraction due to fluctuations in empty space. Between the plates, certain energy waves are excluded, creating a pressure difference that technically suggests negative energy density, but scaling this up to stabilize a wormhole would be like trying to power a starship with an AA battery. The amounts needed are staggering, requiring energies that dwarf planetary outputs. Some calculations suggest a traversable wormhole might need negative energy equivalent to compressing multiple suns into a throat just meters wide. And here's where it gets even trickier. Negative energy isn't just rare, it might come with universe-breaking side effects. General relativity links energy and gravity through Einstein's equations, and negative energy twists this relationship into knots. Could it create time loops or regions where cause and effect unravel? Wormholes lined with exotic matter might not just bridge space, they could rip open paradoxes, challenging the very laws that keep reality predictable. Yet the hunt for solutions is relentless. Some theorists propose tapping into dark energy, the mysterious force accelerating the universe's expansion, as a potential source of cosmic repulsion. Others suggest advanced civilizations might engineer artificial negative energy through quantum field manipulation, bending physics to their will. The audacity of the idea is matched only by its implications. Mastering negative energy wouldn't just open wormholes, it would hand us the keys to spacetime itself. Until then, this remains one of physics' greatest what-ifs, a tantalizing thread connecting the possible to the fantastical. The Morris-Thorne wormhole wasn't just another theory, it was a cosmic blueprint, a step-by-step manual for building a tunnel through spacetime. In 1988, physicists Michael Morris and Kip Thorne took Einstein's equations and did something revolutionary. They didn't just ask if wormholes could exist, they asked how. The result was the first mathematically rigorous design for a traversable wormhole, a structure you could theoretically pass through without being crushed, stretched, or stranded in the void. At the heart of their model lies a breathtakingly simple yet radical idea, a wormhole shaped like an hourglass, with two mouths connected by a smooth, cylindrical throat. Unlike the violent singularities of black holes, Morris and Thorne's design avoids infinite curvature, keeping gravity's tidal forces survivable. But here's the twist, their wormhole doesn't stay open on its own. It needs an invisible scaffold, a lining of exotic matter with negative energy density to counteract the natural collapse. This isn't just rare or unknown material, it's stuff that defies the everyday laws of physics, creating gravitational repulsion instead of attraction. The genius of their approach was in the details. Morris and Thorne didn't just wave their hands at the exotic matter problem, they calculated exactly how much you'd need. Their math showed that stabilizing a 1-meter-wide wormhole throat would require negative energy equivalent to the mass of Jupiter, a daunting number but not an impossible one. Even more striking, they proved such a wormhole could be engineered without violating general relativity, as long as you could somehow gather and manipulate that exotic matter. Their model also tackled another fatal flaw of earlier wormholes, time dilation. Previous theories suggested traveling through a wormhole might spit you out billions of years in the past or future. Morris and Thorne's design included precise constraints to prevent this, ensuring both mouths of the wormhole experience synchronized time critical for anything resembling practical travel. Yet for all its elegance, the Morris-Thorne wormhole remains a paradox. It's a solution that obeys the laws of physics while relying on materials we've never seen. Some researchers argue exotic matter might exist in quantum fields or dark energy, while others think it's a dead end, but their work did something profound. It transformed wormholes from mathematical curiosities into engineering problems. Suddenly, the question wasn't just could they exist, but how could we build one? The legacy of their model echoes through modern physics. It inspired new branches of research, from quantum energy conditions to advanced propulsion concepts. Even if we never find a way to synthesize exotic matter, Morris and Thorne proved one thing: the universe's rulebook might just contain instructions for stitching spacetime itself. Wormholes don't just bend space, they might twist time into knots. Imagine one end of a wormhole anchored near Earth, while the other hurtles off in a starship at near light speed. Einstein's relativity tells us something bizarre happens here. Time slows down for the moving end. After a year on board the ship, decades could pass on Earth. Now step through the wormhole from the ship back to Earth. You'd arrive in your own past. Congratulations, you've just built a time machine. This isn't just theoretical sleight of hand. The math checks out. The faster one end of the wormhole moves, the greater the time differential between its mouths. A traveler hopping through could find themselves in an era before they left, turning science fiction's wildest dreams into hard physics. But there's a catch: time travel brings paradoxes, and the universe hates paradoxes. Take the grandfather paradox: go back in time, prevent your grandfather from meeting your grandmother, and you'd erase your own existence. Yet if you never existed, who went back to meddle with history? It's a logical Ouroboros that threatens to unravel causality itself. Physicists have wrestled with these headaches for decades, and some intriguing solutions have emerged. One compelling idea is the self-consistency principle, which suggests the universe might enforce a kind of cosmic editing. Any attempt to change the past would inherently fail, with your actions somehow reinforcing what already happened. Picture trying to shoot your grandfather, only for the gun to jam or your aim to falter, not by chance, but by the universe bending reality to preserve its own timeline. Another wild proposal involves parallel universes, where time travel doesn't rewrite history but branches it, creating a new timeline where the paradox plays out harmlessly. But wormholes add another layer of complexity. Even if time travel is possible, quantum effects might slam the doors shut. Some models suggest that vacuum fluctuations near a wormhole's throat would amplify into an unstoppable feedback loop, collapsing the tunnel the instant anyone tried to traverse it chronologically. Others argue that exotic matter already needed to stabilize the wormhole might inherently prevent backward time travel, acting as a built-in chrono lock. The deeper we dig, the stranger it gets. Wormhole time travel doesn't just challenge our understanding of physics, it forces us to confront what time even is. Is it an unbreakable arrow, or a pliable dimension we might one day navigate like a highway? Until we detect a real wormhole or unravel quantum gravity's secrets, these questions linger at the edge of science and philosophy. But one thing's certain: if wormholes can manipulate time, the universe is far stranger and far more wondrous than we ever imagined. Black holes have long been cosmic enigmas, bottomless pits where matter vanishes forever. But what if these gravitational monsters aren't endpoints at all? Some theories suggest they could be cosmic turnstiles, their crushing depths masking secret passageways. The idea hinges on a radical reimagining of what lies beyond a black hole's event horizon. Instead of a singularity where physics breaks down, there might be a tunnel threading through space-time, linking to another region of the universe, or another universe entirely. The math behind this is as fascinating as it is counterintuitive. In classical black hole models, crossing the event horizon is a one-way trip spaghettified by tidal forces. You'd inevitably collide with the singularity. But solutions to Einstein's equations, like the Kerr metric for rotating black holes, hint at alternatives. A spinning black hole's inner structure could avoid a true singularity, instead forming a ring-shaped gateway. Pass through it just right, and you might emerge elsewhere, unharmed. The catch: surviving the journey would require navigating violent tidal forces and an environment where time and space swap roles. Misjudge your trajectory, and you'd still hit the ring, obliterated in an instant. This challenges everything we thought we knew about black holes. Traditional models treat them as cosmic dead ends. their gravity so overpowering that not even light escapes. But if they're secretly wormholes in disguise, their role in the universe shifts dramatically. They wouldn't just destroy, they'd transport. Imagine a civilization advanced enough to chart the difference between destructive singularities and traversable ones. They might see black holes not as threats, but as a subway system written into the fabric of reality. Not all physicists are convinced, though. Critics argue that even if black holes hide wormhole throats, the energies required to stabilize them would be unimaginable. Quantum effects near the event horizon, like Hawking radiation or vacuum fluctuations, might collapse any tunnel before it could form. Others point out that without exotic matter to prop open the passage, these wormholes would snap shut faster than a blink. And then there's the biggest hurdle: we have no way to peek inside a black hole to check. Once something crosses the event horizon, it's lost to our observations forever unless it emerges light years away, which we'd never know unless we tried it ourselves. Yet the implications are too staggering to ignore. If black holes are covert wormholes, they could solve some of astrophysics' biggest puzzles: unexplained cosmic rays, matter slipping through hidden tunnels, missing antimatter, shunted to another universe. Even dark matter's elusive nature might hinge on particles traversing these unseen bridges. And if black holes can transform into wormholes under certain conditions, perhaps when they spin fast enough or absorb specific types of matter, it would rewrite our understanding of stellar evolution. The boldest twist comes from theories suggesting black holes don't just contain wormholes, they become them. When a black hole evaporates via Hawking radiation over eons, some models propose it leaves behind not nothingness, but a wormhole's frozen remnant. This cosmic relic, forged from the black hole's spent energy, might linger like a scar in space-time, waiting for some future traveler to reactivate it. Picture a universe littered with these ancient gates, the ashes of dead black holes silently holding the keys to interstellar travel. What makes this theory so compelling isn't just the science, it's the audacity of the shift it demands. Black holes, once the ultimate symbols of cosmic finality, could instead be the universe's grandest infrastructure project. Every galaxy's supermassive black hole might be a central hub in a network we're only beginning to glimpse. The Milky Way's own Sagittarius, a star, could be the subway station at the heart of our galactic city, its entrance hidden in plain sight. Of course, proving any of this remains a monumental challenge. Without a way to test these ideas directly, they linger in the realm of beautiful speculation, but that's the thrill of theoretical physics. Sometimes the wildest ideas are the ones that reshape reality. Whether black holes are cosmic killers or secret gateways, one thing's certain: the universe loves a good plot twist. If wormholes are cosmic shortcuts, then white holes might be their dazzling exit signs, bursting into the universe like reverse black holes, spewing out matter instead of devouring it. These hypothetical twins of black holes have never been observed, but their theoretical existence could solve one of wormhole travel's biggest puzzles: where does the journey end? Picture a black hole's event horizon as a one-way door, swallowing everything that crosses. A white hole would be its mirror image, a door that only opens outward, violently expelling energy and matter with no way back in. Now imagine these two phenomena connected by a wormhole's throat, forming a bridge where entry and exit are locked in perfect, if unstable, harmony. The physics behind white holes is as mesmerizing as it is contentious. Born from the same equations that predict black holes, they emerge when mathematicians flip time's arrow in general relativity. While black holes represent gravitational collapse frozen in time, white holes symbolize explosive rebirth, a region where space itself refuses to let anything enter, only eject. Some theories suggest the Big Bang could have been the ultimate white hole event, a cataclysmic eruption of space-time that birthed our universe from some unknowable elsewhere. If true, it raises a staggering possibility: our entire cosmos might be the exhaust plume of a wormhole linking to another reality. Yet white holes face a glaring problem: they're catastrophically unstable. Unlike black holes, which grow by consuming matter, white holes would theoretically hemorrhage energy, their outward pressure making them prone to rapid disintegration. The moment even a single particle tried to enter, the delicate balance maintaining the white hole could shatter, collapsing it into a black hole. This fragility might explain why we've never detected one. They could blink into existence only momentarily, vanishing before our telescopes catch a glimpse. But what if they're hiding in plain sight? Some astrophysicists speculate that gamma-ray bursts, the most energetic explosions in the universe, could be white holes' dying screams. These fleeting hyperluminous events might mark the last gasp of a wormhole's exit, disgorging accumulated matter in a final, spectacular pulse. Others propose that white holes could masquerade as quasars, their radiant ejecta mimicking the behavior of superheated accretion disks. The challenge is distinguishing them from more mundane cosmic phenomena, a task requiring instruments far beyond today's technology. The most tantalizing idea: white holes might not just be wormhole exits, they could be time-reversed black holes. If a black hole's singularity becomes a white hole's eruption when viewed backward in time, it implies a profound symmetry in the universe's structure. A traveler crossing a black hole's event horizon in one era might emerge from a white hole in another, stitching together a journey that bends not just space, but time itself. This vision turns wormholes into four-dimensional tunnels, where the exit isn't just elsewhere, but elsewhen. Yet skeptics argue white holes are mathematical phantoms, elegant solutions with no physical reality. Without exotic matter or undiscovered physics to stabilize them, they might remain forever trapped in theory, but their potential is too electrifying to dismiss. If white holes exist, they'd rewrite cosmology's rulebook, offering a glimpse of wormholes' far ends, and perhaps revealing where the universe's first travelers truly emerged. What if the universe isn't three-dimensional at all but a colossal hologram? The holographic principle, one of physics' most mind-bending ideas, suggests that all the information in our seemingly three-dimensional cosmos might be encoded on a two-dimensional surface at its boundary. Think of it like a movie projected from a flat screen. Every star, galaxy, and even your own body might just be shadows cast from a hidden, lower-dimensional reality. Now imagine applying this to wormholes. If spacetime itself is a projection, could these cosmic tunnels be glitches in the code? The holographic principle emerged from an unlikely place: black hole thermodynamics. When physicists calculated the maximum entropy a black hole could contain, they found it didn't scale with volume, as you'd expect for a 3D object, but with the area of its event horizon. This bizarre result hinted that all the information swallowed by the black hole might be smeared across its 2D surface like cosmic ink. Extend this idea to the entire universe, and you get a staggering implication. The 3D world we experience could be a rendering of data stored on some distant, flat boundary we'll never see. So where do wormholes fit in? If spacetime is fundamentally two-dimensional, wormholes might not be tunnels at all, but quantum entanglements on the universe's hard drive. Picture two pixels on opposite sides of this cosmic screen suddenly linking up, creating a shortcut through the projected 3D illusion. This perspective could solve one of wormholes' biggest mysteries: how they avoid violating the speed of light. If information isn't actually traveling through 3D space, but just rearranging on the 2D surface, there's no cosmic speed limit being broken, just data being rewritten. Some string theorists take this even further. In certain models, wormholes could be the holographic dual of quantum teleportation. What looks like a space-time tunnel in 3D might correspond to entangled particles exchanging information instantly on the 2D boundary. This would make wormholes less like cosmic subway tunnels and more like glitches where the universe's rendering engine gets confused, stitching together distant points that should never touch. The holographic approach also hints at a radical way to engineer wormholes. Instead of hauling exotic matter across light years, you might program a wormhole by manipulating the underlying information structure. Advanced civilizations wouldn't bend space-time, they'd rewrite it, treating the universe like editable source code. A creature living on the 2D boundary would see this as flipping bits, we'd experience it as a bridge forming between stars. But here's the catch: if wormholes are holographic artifacts, their stability might depend on the universe's resolution. Quantum fluctuations at the smallest scales could make them flicker unpredictably, like a corrupted video file. Traveling through one might feel less like soaring through a tunnel and more like being disassembled into data packets, transmitted and reassembled at the destination. Lose the connection mid-journey, and you might not arrive at all, just scattered bits in the cosmic buffer. This isn't just wild speculation. The holographic principle has already provided solutions to long-standing paradoxes in black hole physics. If it applies to wormholes too, we might need to rethink their very nature not as space-time structures, but as emergent phenomena from a deeper, stranger reality. The universe might not contain wormholes, it might render them on demand whenever the code demands a shortcut, yet the most tantalizing possibility is this: if wormholes connect points in our 3D projection, their endpoints on the 2D boundary could be right next to each other. The vast cosmic distances we see might be an illusion, a trick of perspective from inside the hologram. Unlock this view, and the entire universe could become traversable, not by moving through space, but by realizing space itself was never really there. The ultimate wormhole travel wouldn't require engines or exotic matter, just the understanding that we've been reading reality's source code upside down all along. Einstein's greatest unfinished quest, uniting gravity and quantum mechanics, might hinge on a revelation so elegant, it ties the fabric of spacetime itself to the spooky dance of entangled particles. The R=EPR conjecture, first proposed by physicists Juan Maldacena and Leonard Susskind, dares to suggest that Einstein-Rosen bridges wormholes aren't just analogous to quantum entanglement, they might be the same phenomenon viewed through different lenses. At its core, this idea bridges two of Einstein's most radical contributions: the wormholes predicted by general relativity, and the quantum entanglement he famously dismissed as spooky action at a distance, EPR. What if the universe's most mysterious forces were never separated, all just two sides of a single cosmic coin? To grasp the sheer audacity of this idea, picture two entangled particles, electrons, photons, or any quantum-scale objects. When entangled, measuring one instantly determines the state of the other, no matter how far apart they are. This defies classical intuition, as if information travels faster than light. Now imagine those particles aren't just mathematically linked, but physically connected by a microscopic wormhole, a space-time thread too tiny to see. The R=EPR proposal suggests that what we call entanglement is really a geometric connection, a wormhole in disguise. This would mean every time we observe spooky action, we're unknowingly glimpsing the universe's hidden plumbing. The implications ripple across physics. For decades, gravity and quantum mechanics have resisted unification because they operate on wildly different scales and rules. But if entanglement, a purely quantum phenomenon, is secretly gravitational in nature, it could provide the missing link. Suddenly, the math describing spacetime's curvature and the equations governing quantum weirdness might converge, revealing a deeper layer of reality where geometry and entanglement are interchangeable. Critics argue the conjecture remains speculative, with no direct experimental proof yet, but supporting clues are mounting. In certain string theory models, creating entanglement between two black holes automatically generates a wormhole connecting them. Simulations of quantum systems show behavior eerily similar to gravitational dynamics, as if the universe is hinting at a hidden geometric language. Even more compelling, calculations suggest the amount of entanglement between two regions of space directly corresponds to the area of a wormhole's throat, a numerical harmony that feels too precise to ignore. Yet the most mind-bending twist is how this redefines wormholes themselves. If ER equals EPR, then traversable wormholes might not require exotic matter or cosmic engineering, just enough entanglement. Scaling this up could mean that any sufficiently entangled system particles, stars, even conscious observers, might already be threaded with microscopic wormholes, weaving the universe into a vast, invisible network. The cosmic web we see in galaxy clusters, perhaps just the visible nodes of a far deeper entanglement, with spacetime itself as the emergent pattern. This conjecture doesn't just solve puzzles, it ignites new ones. If wormholes and entanglement are identical, could we manipulate one by controlling the other? Might quantum computers someday engineer spacetime by entangling particles in precise configurations? And if entanglement creates spacetime, what does that say about the nature of reality itself? The R equals EPR idea is more than a theory, it's a doorway, and on the other side, the universe might look nothing like we thought. String theory rewrites the rules of reality by proposing that the universe isn't just four-dimensional, it's a symphony of 10 or more dimensions, curled into shapes so tiny we'll never perceive them directly. But hidden within this labyrinth of extra dimensions might lie the ultimate cheat code for wormhole travel. Unlike traditional models that squeeze wormholes into the familiar fabric of spacetime, string theory offers a playground where higher dimensions could harbor stable, navigable tunnels, if we know where to look. At the heart of this possibility are Calabi-Yau manifolds complex, multi-dimensional shapes that string theory suggests could compactify the extra dimensions around us. Picture a garden hose. From a distance it looks like a simple line, but zoom in and you'll find it's actually a cylinder. Calabi-Yau manifolds take this idea to cosmic extremes, curling 6 extra dimensions into intricate, knotted geometries at every point in space. These shapes aren't just mathematical curiosities, they could be the scaffolding for wormholes. Some configurations might naturally contain microtunnels threading through the extra dimensions, shortcuts bypassing our three-dimensional reality entirely. Traveling through one would be like a flea crawling through the coiled folds of a hose, instead of marching along its length, a detour through unseen terrain. But the real game-changer comes with brains, short for membranes. In string theory, our entire universe might be a three-dimensional brain floating in a higher dimensional bulk. Other brains could hover mere millimeters away in these extra dimensions, forever invisible because light and matter are stuck to our brain like flies on wallpaper. Here's where wormholes get interesting. If two brains warp toward each other in the bulk, their connection might form a throat-like wormhole, bridging not just locations in space but entire parallel universes. The energy required to pry brains apart could stabilize the tunnel, eliminating the need for exotic matter. Critics argue these ideas are untestable for now. Calabi-Yau manifolds exist at scales trillions of times smaller than atoms, and detecting brain collisions would require energies far beyond our particle colliders. Yet the math is tantalizing. Certain string theory solutions describe wormholes where quantum fluctuations in the extra dimensions counteract gravitational collapse, effectively self-stabilizing the tunnel. Others suggest that advanced civilizations might manipulate brain dynamics like cosmic engineers, folding spacetime to create wormholes on demand, the boldest implication. If string theory's extra dimensions host wormholes, our universe might be threaded with them already, not as rare anomalies, but as fundamental features of reality's architecture. Every particle collision, every star's death, could momentarily twist these hidden dimensions into ephemeral tunnels. Mastering them wouldn't just revolutionize travel, it would unveil the universe's secret blueprints, proving that the dimensions we can't see hold the keys to everywhere. Dark matter has been the universe's most frustrating puzzle, an invisible substance weaving through galaxies, binding them together with its gravitational pull, yet refusing to reveal its true nature. But what if this cosmic ghost isn't just holding stars in place? Some theorists propose it might be the ultimate power source for wormholes, a hidden fuel capable of propping open spacetime's most elusive tunnels. The logic behind this idea hinges on dark matter's strangest qualities. Unlike ordinary matter, it doesn't interact with light or electromagnetic forces. It's detectable only through its gravitational footprint. This same aloofness could make it the perfect exotic matter candidate. Wormholes, as Einstein's equations describe them, need something with negative energy or repulsive gravity to counteract their natural collapse. Dark matter's gravitational behavior already bends the rules. Some models suggest certain types could exhibit precisely the anti-gravitational effects required to stabilize a wormhole's throat. Imagine a form of dark matter that doesn't just pull but pushes, creating a cosmic cushion to keep the tunnel from snapping shut. The variants of dark matter that could fit this role are as speculative as they are fascinating. Action's hypothetical ultralight particles might interact in ways that generate negative pressure under extreme conditions, or sterile neutrinos, heavier and even more elusive cousins of standard neutrinos, could cluster in wormhole throats, their quantum properties twisting gravity into a stabilizing force. The most radical proposals involve mirror matter, a shadowy duplicate of our own particles, invisible yet gravitationally present. If such matter exists, it might naturally form the scaffolding for wormholes, threading the universe with unseen bridges. Yet the leap from theory to reality is vast. For starters, we've never directly detected dark matter, let alone confirmed its detailed properties. Assuming it could stabilize wormholes requires extrapolating far beyond current evidence, into realms where particle physics and general relativity collide in uncharted ways. Even if dark matter has the right traits, harvesting and manipulating, it would demand technologies far beyond our grasp. Imagine trying to bottle a substance that slips through solid matter like wind through a sieve. There's another twist. Dark matter's distribution might make wormholes wildly unpredictable. Most models assume it's clumped in halos around galaxies, but if it's concentrated in dense filaments or primordial black holes, traversable wormholes could lurk in regions we'd never think to search. Picture a wormhole hidden in the dark matter web between galaxies, its entrance invisible until some unlucky starship stumbles into its gravitational embrace. The universe's highways might already be built, we just can't see the on-ramps. Skeptics counter that dark matter's role is pure conjecture, without proof that it can generate negative energy or curve spacetime in the necessary ways. The idea remains a tantalizing what if. Yet the same uncertainty that makes it controversial also fuels its allure. If even a fraction of dark matter's hypothetical forms possess the right properties, the implications rewrite the rules of interstellar travel. Wormholes wouldn't be rare anomalies, they'd be as common as the unseen matter saturating the cosmos, waiting for a civilization clever enough to map the darkness. The boldest take, dark matter's true purpose might be architectural. If the universe is teeming with wormholes stabilized by this shadowy substance, it suggests a design far more intricate than we've imagined. The matter we see, stars, planets, even ourselves, could be mere decorations on a scaffold built from something we can't perceive. Unlocking dark matter's secrets wouldn't just solve a cosmic mystery, it might hand us the keys to the universe's hidden doorways. The early universe wasn't just hot and dense, it might have been tangled. In the chaos of the Big Bang, spacetime itself could have knotted into bizarre defects, flaws frozen into the fabric of reality like cracks in cooling glass. Among these relics, none are stranger than cosmic strings, hypothetical filaments thinner than an atom yet stretching across the universe, heavier than entire galaxies, and capable of bending space so violently they might twist it into wormholes. These strings aren't made of matter, they're spacetime itself tied into knots. Picture the universe moments after its birth, a seething quantum foam where fundamental forces hadn't yet settled into their current forms. As symmetry broke and the cosmos cooled, Regions where this transition happened unevenly might have formed one-dimensional scars. These scars would be unimaginably dense, concentrated mass energy with no thickness, yet exerting gravitational pull so intense they'd warp the space around them like a taut wire cutting into foam. Under the right conditions, two parallel cosmic strings accelerating away from each other could stretch space-time between them so severely that it pinches shut, forming a bridge between two distant points. Voila, a wormhole stitched together by cosmic defects. What makes cosmic strings such compelling wormhole architects is their gravitational uniqueness. Unlike black holes or stars, their extreme mass isn't concentrated in a sphere but stretched into an infinite line. This creates a gravitational field that drops off more slowly with distance, allowing them to bend spacetime in ways ordinary matter can't. Two strings moving at relativistic speeds could generate a time-dilated corridor between them, a natural if unstable wormhole. Some models even suggest that closed loops of cosmic strings, snapping apart like overstretched rubber bands, might briefly create microscopic wormholes as they vanish in a burst of gravitational waves. But finding evidence for these space-time stitches is a challenge. Cosmic strings would be nearly invisible, only betraying their presence through subtle lensing effects, light bending around them as if passing through an unseen prism. Some astronomers search for telltale kinks or cusps in the cosmic microwave background, the afterglow of the Big Bang, where a string's passage might leave faint thermal scars. Others hunt for abrupt, duplicate images of distant galaxies, a sign that a string's immense gravity is splitting light like a cosmic fork in the road. The most tantalizing possibility: if cosmic strings exist, they might have already woven wormholes into the universe's fabric during its infancy. These primordial tunnels wouldn't require exotic matter or advanced engineering. They'd be artifacts of spacetime's turbulent birth, lurking between galaxies like submerged cave systems. A civilization that could locate and stabilize them wouldn't just exploit wormholes, they'd inherit a network built by the universe itself, a relic of creation's first moments waiting to be rediscovered. General relativity paints spacetime as a smooth, unbroken fabric, but what if that fabric is woven from tiny, indivisible threads? Loop quantum gravity dares to rewrite Einstein's vision, proposing that spacetime isn't continuous at all. Instead, it's built from microscopic loops and networks, a pixelated reality where even emptiness has structure. In this radically different universe, wormholes wouldn't form from warped smoothness, they'd emerge from the quantum knots tying spacetime itself together. The key lies in how loop quantum gravity handles the nightmare singularity at a black hole's heart, where general relativity predicts infinite density and crushed physics. Loop theory suggests quantum effects prevent total collapse. Spacetime's discrete grains act like a cosmic safety net, stopping gravity's crushing grip just short of infinity. This transforms the singularity into a portal, a tunnel through spacetime's quantum weave. Without infinite curvature to sever the wormhole's throat, these tunnels could remain stable enough to traverse, no exotic matter required. Compare this to classical wormholes in general relativity, where smooth spacetime must warp violently to form a tunnel. The equations demand infinite forces or impossible materials to keep the passage open, but in loop quantum gravity, wormholes might arise naturally from spacetime's granular structure. Picture a densely knitted sweater, pull two distant stitches close enough, and the threads between them form a tiny bridge. On the Planck scale, spacetime could behave similarly, with quantum loops occasionally braiding into shortcuts between far-flung regions. This quantum stitching solves another notorious problem, the firewall paradox. Traditional wormholes risk incinerating travelers with deadly radiation at the midpoint due to quantum effects. But if spacetime is inherently granular, those violent fluctuations might smooth out, like stepping stones stabilizing a raging river's crossing. Simulations in loop quantum cosmology already show collapsing black holes rebounding into white holes, a process that could forge wormholes as cosmic byproducts. Yet loop quantum wormholes come with their own mysteries. If spacetime is discrete, traversing a wormhole might feel less like gliding through a tunnel and more like teleporting between quantum pixels. The journey could involve abrupt jumps, with the traveler's information rewritten across spacetime's fundamental lattice. Some models even suggest these wormholes would inherently link to parallel universes, as the quantum network extends beyond our observable reality. The greatest promise of this approach, it unites wormholes with quantum mechanics seamlessly, where general relativity treats them as alien structures requiring exotic engineering. Loop quantum gravity suggests they're woven into reality's blueprint. The universe's first wormholes might not have been cosmic accidents, they could be inevitable features of spacetime's quantum architecture, waiting for a theory bold enough to predict them. Quantum tunneling defies common sense, particles vanishing through barriers they shouldn't, appearing on the other side like ghosts slipping through walls. Now stretch that phenomenon across light years, and you've got wormholes as nature's ultimate quantum loophole. If subatomic particles can cheat physics on tiny scales, could spacetime itself pull off the same trick in the cosmic arena? This theory proposes that wormholes aren't just cosmic structures, they're quantum tunneling events writ large, spacetime's fleeting moments of rebellion against its own rules. At the quantum level, tunneling happens because particles don't have definite positions, they exist as probability clouds. There's always a minuscule chance an electron will materialize on the far side of an impenetrable barrier, as if teleporting. Scale this up to wormholes, and you're dealing with probabilities so vanishingly small they make winning the lottery look inevitable. Yet in an infinite universe, even the rarest events occur somewhere. A spontaneous wormhole might flicker into existence by sheer quantum luck, connecting two distant points before collapsing faster than a camera's shutter click. Harnessing such randomness for travel sounds impossible, but quantum physics offers a glimmer. Some interpretations suggest observing a quantum system locks it into a definite state. Apply this macroscopic scale, and a conscious observer might stabilize a wormhole simply by detecting it, freezing its fleeting existence into something navigable. It's like the old thought experiment: if a tree falls in a quantum forest and nobody's there to hear it, did it tunnel through a mountain first? The act of measurement could transform probability into permanence. Critics argue the energy scales don't add up. Quantum tunneling works for particles because their wavelengths are comparable to atomic distances. A wormhole big enough for a proton would require probabilities so low, the universe hasn't existed long enough for it to happen once. Yet string theory's hidden dimensions or vacuum fluctuations might tweak the math, nudging those impossible odds into the realm of plausibility. Imagine a civilization that couldn't create wormholes, but learned to predict where they'd randomly appear, like surfers riding rare waves in spacetime's quantum foam. The wildest implication: if wormholes are quantum events, they might not obey deterministic cause and effect. Stepping through one could sever your connection to a predictable universe, ejecting you into a realm where reality reshuffles itself with every observation. Forget maps, you need probability matrices to navigate. This isn't just travel, it's reality hopping, with the universe rolling cosmic dice at every turn. Yet buried in this chaos is a tantalizing pattern. If all quantum particles are intrinsically linked through fields, perhaps spacetime itself shares that interconnectedness. Wormholes wouldn't be anomalies, they'd be spacetime remembering its quantum roots, briefly acting as the entangled universe it truly is. The first travelers might not conquer wormholes, they'd learn to think like them, speaking probability fluently enough to whisper spacetime into stability. What if every wormhole is a backdoor to another universe? The multiverse hypothesis, once relegated to science fiction, now stands as one of cosmology's most electrifying possibilities, and wormholes might be the secret tunnels stitching these alternate realities together. Imagine a vast cosmic foam, where each bubble represents a self-contained universe with its own unique physics, history, and even versions of you. Wormholes could pierce through the membrane separating these bubbles, creating bridges where none should exist. This isn't just about traveling across space, it's about slipping between the very foundations of existence. The physics behind this idea emerges from inflation theory, which suggests our universe expanded exponentially in the first fraction of a second after the Big Bang. Some models propose this inflation never truly stopped, it just slowed in our local region, while other patches of spacetime kept stretching, birthing endless bubble universes. These bubbles would naturally repel each other, drifting apart in an ever-expanding multiverse, but wormholes could defy this isolation. Picture two soap bubbles pressed together. If a needle pierces both, it creates a passage linking their interiors. In cosmic terms, a wormhole threaded with exotic matter might serve as that needle, tethering universes that would otherwise never touch. The implications are dizzying. A multiverse-traversing wormhole wouldn't just require stability, it would need to navigate radically different physical laws. One universe might have stronger gravity, another might permit faster than light travel as the norm. Crossing through could mean encountering matter that behaves in ways our physics can't describe. Some theories even suggest certain wormholes might function as cosmic translators, reshaping particles and energy to match the destination universe's rules. A traveler stepping through might emerge with their atoms subtly reconfigured, their very biology adapted to the new reality's constants, yet the challenges are as colossal as the possibilities. Bubble universes aren't just distant, they're separated by unfathomable energy barriers. The space between them isn't empty, it's a seething false vacuum, a realm where the fundamental forces have different strengths. A wormhole spanning this divide would need to withstand forces that could unravel spacetime itself. Some calculations suggest the energy required might exceed the output of entire galaxies, making multiverse travel a feat only conceivable for civilizations wielding power beyond our imagination. Here's where the science bends toward philosophy. If wormholes connect parallel universes, do they also link alternate timelines? Could a traveler enter a universe where the dinosaurs never went extinct, or where humanity took a different evolutionary path, the branching paths of quantum mechanics, where every decision spawns new realities, might converge in a vast network of wormholes, turning the multiverse into an interconnected web rather than isolated bubbles. Critics argue this remains speculative fiction without experimental proof, but tantalizing hints linger at the edges of physics. Anomalies in cosmic microwave background, data unexplained cold spots, or unusual patterns could theoretically be scars from long-vanished wormholes brushing against our universe. Others propose that quantum entanglement, where particles instantaneously influence each other across distances, might be the microscopic echo of a multiversal wormhole structure. If particles can be entwined through higher dimensions, why not entire universes? The boldest take, wormholes might not merely connect universes, they could birth them. A black hole collapsing in our universe might spawn a white hole in another, creating a bridge that becomes a new cosmic bubble seed. In this vision, every wormhole is a potential universe in its own right, a cosmic umbilical cord linking parent and child realities. The first travelers through a multiversal wormhole wouldn't just discover new worlds, they might witness creation itself, unfolding in infinite variations across the tapestry of existence. When neutron stars spiral toward their doom, they don't just collide, they twist the fabric of reality into knots. These ultra-dense stellar corpses, packing a sun's worth of mass into a city-sized sphere, generate gravitational forces so extreme they briefly warp spacetime like taffy. Most models assume these cataclysmic mergers end in black holes or hypermassive neutron stars, but there's a tantalizing alternative. For a fraction of a second during the collision, the sheer violence of the event might punch a hole through spacetime itself, birthing a wormhole too short-lived to traverse but real enough to leave scars in the universe's ledger. The physics behind this possibility hinges on the neutron star's absurd density. At their cores, matter gets compressed beyond atomic structure, collapsing into a quantum soup where neutrons overlap like sardines in a cosmic can. When two such stars merge, their combined gravity spikes to levels rivaling black holes, but with a crucial difference. Unlike the orderly collapse of a single massive star, the chaotic dance of merging neutron stars sends shockwaves through spacetime, creating turbulence that could momentarily stitch together a wormhole's entrance and exit. Picture two whirlpools colliding in a bathtub. The interference pattern between them might briefly open a drain connecting distant points in the water. Detecting such an event would require instruments sensitive enough to catch spacetime's subtle hiccups. Enter gravitational wave observatories like LIGO and Virgo. These detectors have already recorded neutron-star mergers by measuring the ripples they send through spacetime, but what if some collisions leave more than just waves? Certain gravitational wave signatures could betray a wormhole's fleeting presence. A telltale wobble in the signal's decay, an anomalous echo, or an extra spike in the waveform might hint at spacetime briefly pinching into a tunnel before snapping back. Some theorists even suggest wormholes would produce high frequency after ringing in the data, like a bell tolling from the other side of a cosmic door. Yet skeptics argue these signals could have mundane explanations: turbulence in the merging stars, quark-gluon plasma, or resonance effects from their rapidly spinning remnants. The smoking gun would be evidence of matter or energy somehow bypassing the expected gravitational constraints, like gravitational waves arriving microseconds too early, as if taking a shortcut. Even more compelling would be detecting identical gamma-ray bursts from different points in the sky nearly simultaneously, a potential sign of a wormhole splitting a signal into multiple exits. The most intriguing possibility: if neutron star wormholes exist, even ephemerally, they might seed the universe with quantum entanglement on a macroscopic scale. Particles separated by the wormhole's brief bridge could remain mysteriously linked, their fates intertwined across light years. It's as if the universe itself gets tangled in the aftermath, leaving behind ghostly connections where a tunnel once stood. This theory doesn't just challenge our understanding of neutron stars, it turns them into potential architects of cosmic infrastructure. A civilization advanced enough to predict and harness these events might not need to build wormholes at all. Instead, they could lie in wait near merging neutron stars, ready to surf the spacetime ruptures that nature provides. The key to interstellar travel might not be engineering, but timing. Next time you hear about the searing jets of quasars lighting up the cosmos, consider this: those swirling maelstroms of plasma might be doing more than just shining. They could be twisting spacetime into shapes that mimic wormholes. Plasma, often called the fourth state of matter, behaves like a fluid but conducts electricity, allowing magnetic fields to sculpt it into structures that defy intuition. When you cram enough energy into plasma, like the superheated soup around black holes or in the hearts of quasars, it starts bending spacetime in ways eerily similar to theoretical wormholes. Lab experiments are already chasing this possibility. In facilities like the Lawrence Livermore National Laboratory or the Large Hadron Collider, physicists blast plasma with lasers or magnetic fields to create extreme conditions rivaling those near neutron stars. Under these pressures, the plasma's charged particles generate electromagnetic fields so intense they warp spacetime itself, creating fleeting regions where the fabric of reality briefly buckles. Some models suggest these warps could, under precise conditions, form microscopic bridges, effectively wormholes in a test tube. The resemblance isn't just mathematical. Quasars, those cosmic lighthouses powered by supermassive black holes, spew plasma jets moving at nearly the speed of light. These jets aren't just chaotic, they're threaded with helical magnetic fields, spiraling like DNA. That structure mirrors some wormhole solutions in general relativity. where twisted magnetic fields could stabilize a tunnel's throat. If nature's most violent plasma phenomena already create these configurations, could they be accidentally or intentionally forming traversable shortcuts? Here's where lab work gets thrilling. In 2019, researchers at Princeton's Plasma Physics Laboratory generated a plasma structure with a magnetic knot, a topology that mathematically resembles a wormhole's entrance. Though it lasted mere nanoseconds, it proved that even earthly plasmas can mimic spacetime's most exotic contortions. Other teams are using high-powered lasers to induce plasma wakes, regions where waves in the charged soup could, in theory, curve spacetime enough to pinch it into a bridge. The goal isn't just academic mastering. These effects might reveal how to engineer stable wormholes using tools we already have, rather than mythical, exotic matter. Critics argue plasma wormholes would be too unstable for travel, collapsing before anything could traverse them, but supporters counter that natural cosmic plasmas might self-stabilize through feedback loops we don't yet understand. After all, if black holes can eject plasma jets spanning galaxies, who's to say those jets don't hide spacetime tunnels in their cores? The next generation of plasma experiments, coupled with gravitational wave detectors, could spot the telltale tremors of a plasma-borne wormhole flickering into existence. The most tantalizing thought: if plasma can bend spacetime this way, the universe might be littered with accidental wormholes formed in the hearts of stars, the aftermath of supernova, or the jets of active galaxies. We've been staring at them for centuries, mistaking them for mere fireworks in the cosmic dark. Dark energy isn't just pushing galaxies apart, it might be the invisible hand propping open the universe's hidden doorways. This mysterious force, responsible for accelerating the cosmos expansion, shares an eerie similarity with the exotic matter needed to stabilize wormholes. It generates gravitational repulsion. While dark energy stretches spacetime on cosmic scales, could it also be warping it into tunnels on smaller, more navigable levels? The collision of these two ideas, dark energy's relentless push and wormholes' need for anti-gravity, could rewrite our understanding of cosmic shortcuts. Take a closer look at the numbers. Dark energy accounts for roughly 68% of the universe's total energy budget, dwarfing everything from stars to black holes. Its repulsive effect isn't just strong, it's growing as the universe expands, dominating gravity's pull over vast distances. Now imagine harnessing even a fraction of that power to counteract a wormhole's collapse. Instead of requiring exotic matter synthesized in labs or mined from quantum anomalies, the energy needed to prop open a traversable tunnel might already be saturating the cosmos, woven into the fabric of empty space itself. The key lies in manipulating its distribution, concentrating dark energy's push into specific regions where spacetime needs reinforcement. This isn't just theoretical sleight of hand. Some solutions to Einstein's equations suggest that dark energy's influence could naturally deform spacetime into structures resembling wormholes over astronomical timescales. Picture the universe's expansion not as a uniform stretching, but as a tapestry with threads occasionally knotting into loops. Regions where dark energy's repulsion becomes slightly anisotropic, stronger in one direction than another, might pinch spacetime into bridge-like formations. These wouldn't be the neat, cylindrical wormholes of sci-fi. They'd be dynamic, unstable structures, constantly reshaped by the competing forces of cosmic expansion and local gravity. Yet the challenges are as vast as the potential. Dark energy's density is absurdly low, about 1 joule per cubic kilometer of space. Stabilizing even a meter-wide wormhole throat would require compressing dark energy equivalent to a galaxy cluster's worth of volume into that tiny region. The engineering hurdles are mind-bending, but not insurmountable. Advanced civilizations might exploit dark energy's quantum underpinnings, manipulating vacuum fluctuations to amplify its effects in localized areas. Others speculate that certain spacetime geometries, like the intricate folds around rotating black holes, could naturally focus dark energy into wormhole, sustaining configurations without artificial intervention. The wildest implication, dark energy's influence changes over time. Billions of years from now, as the universe's expansion approaches exponential speeds, dark energy could dominate so completely that spacetime itself begins to fracture. In this distant era, wormholes might form spontaneously, their throats inflated by the cosmos' runaway stretching. Travelers then wouldn't need to build wormholes, they'd simply wait for the universe to unravel into a network of tunnels. Until then, dark energy remains a tantalizing enigma. The force that's silently sculpting the universe's fate might also hold the blueprint for its ultimate transportation system. Critics argue that dark energy's uniformity makes it useless for wormhole engineering. Its repulsion appears perfectly balanced across space, leaving no natural gradients to exploit. But anomalies in recent cosmic acceleration measurements hint at possible variations, pockets where dark energy behaves differently. If these irregularities exist, they could mark the locations of naturally occurring spacetime bridges, cosmic backdoors forged by the universe's own expansion. The deeper mystery lies in dark energy's true nature. Is it a property of empty space, as Einstein's cosmological constant suggests, or a dynamic field that fluctuates, like the inflation that powered the Big Bang? If the latter, wormholes could be its unintended byproducts, shadows cast by a force we're only beginning to comprehend. Unlocking this connection wouldn't just open new paths through space, it would reveal that the universe's most elusive component has been quietly shaping its hidden architecture all along. Quantum entanglement has always felt like magic, particles instantly influencing each other across vast distances, defying the speed of light. But what if this spooky action isn't just a connection through space, but a physical tunnel woven into spacetime itself? The R equals EPR conjecture takes Einstein's two greatest paradoxes, wormholes and entanglement, and merge them into a single breathtaking idea. Every pair of entangled particles might be linked by a microscopic wormhole, a spacetime thread too tiny to see yet binding the universe together at its most fundamental level. This radical notion flips how we imagine quantum links. Traditionally, entanglement is described mathematically. Particles share a quantum state, and measuring one instantly determines the other, no matter how far apart. But if ER equals EPR holds that math could map onto real geometry, the particles aren't just abstractly correlated, they're physically tethered by a Planck-scale wormhole. Picture two electrons entangled in a lab. Under this theory, their connection isn't some invisible signal, it's a submicroscopic bridge warping spacetime between them, a shortcut so small even atoms would dwarf it. Testing this idea isn't just theoretical play. Quantum teleportation experiments where particle states are transmitted across distances using entanglement might already be inadvertently probing these spacetime threads. When scientists teleport quantum information from one photon to another, could they actually be exploiting a wormhole's geometry? Recent breakthroughs in holographic quantum simulations support this. By programming quantum computers to mimic entangled systems, researchers found the math describing their behavior eerily mirrors equations for traversable wormholes. It's as if the universe is hinting that entanglement's abstract links and spacetime's physical bridges are two sides of the same coin, yet skepticism remains. Critics argue that equating entanglement with wormholes stretches the metaphor too far, like saying a shadow is the same as the object casting it. After all, no one's directly observed a wormhole's spacetime structure in the lab. But supporters counter that the duality might only become obvious at extremes, perhaps only when entanglement scales up dramatically, like between black holes, does the wormhole's geometry visibly emerge. The boldest experiments now aim to force this link into the open. Some teams are designing quantum systems where entanglement can be precisely tuned, watching for gravitational side effects, tiny spacetime warps that shouldn't exist unless ER equals EPR is real. Others are probing whether manipulating entangled particles alters local spacetime curvature, even minutely. If successful, these tests wouldn't just confirm a theory, they'd prove that the universe's quantum rules and gravitational fabric are inseparably intertwined. Imagine the implications. If every entanglement traces back to a wormhole, then the universe is far more connected than we thought, not just through abstract probabilities, but through a labyrinth of invisible spacetime threads. Master this, and quantum communication could become literal teleportation, with information racing through hidden dimensions rather than across space. The first civilization to harness this wouldn't just exploit entanglement, they'd ride the universe's hidden subway, where every quantum link is a ticket to somewhere else. Supersymmetry whispers a tantalizing promise. What if every particle we know has a hidden twin? This elegant theory, known as SUSY, proposes a shadow universe of undiscovered particles that could solve physics' greatest puzzles. Among their speculative powers, they might be the exotic matter holding wormholes open. While the Large Hadron Collider hasn't yet spotted these superpartners, their hypothetical properties align eerily with the antigravity needed to stabilize spacetime's most elusive tunnels. Picture the supersymmetric Zeus electrons partnering with electrons, squarks mirroring quarks, all with spins tweaked just enough to balance the universe's quantum books. Some of these particles, like the gravitino or neutralino, could possess negative energy densities under specific conditions. Their quantum interactions might generate the gravitational repulsion required to prop open a wormhole throat, counteracting the crushing weight of spacetime's natural curvature. Unlike hypothetical dark matter candidates, SUSY particles' behaviors are mathematically precise, offering physicists calculable pathways to engineering stability rather than relying on cosmic luck. The math gets even more intriguing when you consider R parity, a proposed symmetry that prevents supersymmetric particles from decaying too quickly. Certain R parity violating models allow selectrons or neutrinos to form macroscopic structures, clusters dense enough to line a wormhole's interior like cosmic rebar. These wouldn't just resist collapse, they might actively repel each other through spin-mediated forces, creating a self-sustaining antigravitational lattice. Yet SUSY allure hides a glaring problem. Decades of particle collider searches have found no trace of superpartners. The LHC's failure to detect them at predicted energy scales has left many physicists skeptical. If supersymmetry exists, its particles must be far heavier than initially hoped, pushing them out of practical reach for current technology. Some theorists argue this isn't a death blow, just a recalibration. Perhaps SUSY particles manifest only at energies approaching the Planck scale, or in higher dimensions. Others suggest the missing superpartners might be hiding in plain sight, camouflaged as dark matter or masquerading as quantum vacuum fluctuations. Even unconfirmed, SUSY framework offers wormhole engineering something priceless: testable parameters. Unlike vague exotic matter conjectures, supersymmetry provides precise mass ranges and coupling strengths. Future colliders like the proposed 100-kilometer Future Circular Collider could probe these energy frontiers, either discovering SUSY particles or finally retiring the theory. Until then, supersymmetry remains the most rigorously quantified, maybe in physics, a ghostly scaffold for wormholes that might vanish with the next experiment or solidify into reality. The boldest twist: if SUSY particles do exist but evade detection because they interact solely through gravity, they could be threading the universe right now, invisible yet omnipresent. Wormholes stabilized by such matter wouldn't need to be built, they'd already exist, woven into spacetime's fabric, waiting for a civilization clever enough to map gravity's subtlest whispers. Vacuum decay sounds like science fiction, but it might be the universe's ultimate self-destruct button. At its heart lies a terrifying possibility: our entire reality could be sitting in a precarious state, a bubble of stability in an otherwise unstable cosmos. In wormholes, those hypothetical spacetime tunnels, might just be the needles capable of popping that bubble. When physicists talk about vacuum decay, they're describing a scenario where a random quantum fluctuation or an intentional intervention triggers a catastrophic phase transition, rewriting the fundamental constants of nature. Now imagine that trigger being pulled by a wormhole's immense gravitational forces, unleashing a wave of annihilation that races outward at light speed, erasing physics as we know it. This doomsday mechanism hinges on the nature of the quantum vacuum. Far from empty, what we call empty space is actually a seething quantum field, brimming with potential energy. Think of it like a ball resting atop a hill seemingly stable, but one nudge from falling into a lower energy state. Our current laws of physics depend on this delicate balance. But if something, say, the extreme curvature near a wormhole's throat provides that nudge, the vacuum could collapse into a more stable configuration. The moment this decay begins, it creates an expanding wall of destruction where matter itself unravels, atoms lose cohesion, and even the concept of light changes. The universe as we know it wouldn't just end, it would be replaced. Wormholes amplify this risk because they're gravitational anomalies. The intense warping near their throats could lower the energy barrier keeping the vacuum stable, making the unthinkable probable. Picture a lightning rod during a storm. The wormhole doesn't create vacuum decay, but it might attract the conditions that spark it. Some models suggest that traversable wormholes, those propped open by exotic matter, are especially risky, as their artificial stabilization could destabilize the quantum fields around them. It's the ultimate cosmic irony. The very technology that enables interstellar travel might also erase the destinations, yet the odds are astronomically low. For vacuum decay to trigger, the wormhole would need to form in a very specific energy state, under precise conditions that currently exist only in theoretical equations. The universe has lasted 13.8 billion years without this cataclysm, suggesting either that natural wormholes avoid these parameters, or that we've been lucky. But low probability doesn't mean zero. If an advanced civilization were to engineer wormholes without fully understanding vacuum metastability, their experiments could inadvertently doom not just their world, but the entire cosmos. The most chilling aspect, we might not see it coming. A vacuum decay event would propagate at light speed, giving no warning before it reached us. One moment the universe operates as usual, the next, physics as we know it ceases to exist. Wormholes capable of triggering this wouldn't just be dangerous, they'd be the ultimate ecological violation, risking reality itself for the sake of shortcuts through space. Yet buried in this apocalyptic scenario is a strange hope. If vacuum decay can be triggered artificially, it might also be prevented or even harnessed. Some fringe theories suggest a sufficiently advanced civilization could firewall their region of space-time against decay, or even guide the phase transition to rewrite physics in their favor. Wormholes wouldn't be doomsday devices, but tools for cosmic rebirth. The same tunnel that risks annihilation could, with flawless precision, become a lifeline bridging not just space, but universes with entirely different fundamental laws. This is the razor's edge wormhole physics walks. The power to bend spacetime doesn't just come with engineering challenges, it carries existential stakes. Vacuum decay forces us to confront a sobering truth. Some doors, once opened, can't be closed, and the universe's first wormhole travelers might not just be explorers. They could be gamblers, betting reality itself on the chance to go farther than anyone thought possible. Hawking's black hole information paradox isn't just a puzzle, it's a tear in the fabric of physics itself. The problem starts simply: when a black hole evaporates through Hawking radiation, what happens to all the information it swallowed? Quantum mechanics insists information can never be destroyed, yet general relativity claims it's irretrievably lost behind the event horizon. This clash has haunted physicists for decades, threatening to undermine our understanding of reality. but wormholes might stitch the rift closed, offering a cosmic backdoor where information slips away safely instead of vanishing forever. At the heart of this solution lies the holographic principle, the idea that all the information within a volume of space can be encoded on its boundary, like a 3D movie projected from a 2D screen. Apply this to black holes, and the information they consume might not vanish into the singularity, but linger smeared across the event horizon. Now add wormholes to the equation. If a black hole's interior connects to another region of spacetime via a microscopic wormhole, that information could be secretly routed elsewhere, preserved but hidden from our view. It's like burning a book in one room only to discover its words were etched into the walls of another dimension all along. The math gets even wilder when you consider quantum entanglement. If wormholes are the geometric manifestation of entanglement, as the R equals EPR conjecture suggests, then every particle of Hawking radiation emitted by a black hole could be invisibly linked to its interior through spacetime threads. Information wouldn't be lost, it'd be scrambled across this labyrinth of connections, waiting to reassemble when the black hole fully evaporates. Imagine a jigsaw puzzle scattered not across a table, but across parallel universes. Only a wormhole's lens could reveal the complete picture. Critics argue this merely relocates the paradox. If information exits via wormholes, where does it go? Some theories propose it emerges in a baby universe, branching off from our own like a cosmic exhale. Others suggest it's encoded in the Hawking radiation itself, with wormholes acting as quantum error-correcting channels that prevent data loss. The most radical idea, black holes might be factories for spacetime itself, with every bit of swallowed information fueling the creation of new wormholes and tunnels that don't just preserve information but multiply it, weaving a growing tapestry of interconnected realities. Yet the stakes are higher than academic curiosity. If wormholes resolve the information paradox, they'd force us to rewrite textbooks from particle physics to cosmology. The universe wouldn't be a collection of isolated events, but a dynamic network where every black hole is a node in a vast informational web. Lose a star to a singularity, and its essence might still hum through hidden bridges, echoing in corners of the cosmos we've yet to map. The paradox's potential solution also hints at wormholes' fragility. If they're cosmic hard drives preserving information, tampering with them could risk data corruption on a universal scale. Picture a civilization attempting to traverse a black hole's wormhole, only to disrupt the delicate entanglement sustaining the information flow. The result: not just a failed expedition, a rupture in spacetime's memory, where causality itself begins to glitch. While we lack the tools to observe this directly, clues might lurk in the afterglow of black hole mergers. Gravitational wave detectors could one day spot anomalies in collision, echo subtle signatures of information, sneaking through microscopic wormholes rather than dying with the singularity. Until then, the paradox remains a beacon, guiding us toward a deeper truth. Wormholes might not just connect space, they could be the universe's way of remembering itself. Our three-dimensional world might just be the tip of the cosmic iceberg. What if wormholes aren't hiding within our familiar space, but coiled within dimensions we can't perceive? Theories like Kaluza-Klein and Brainworld models suggest higher dimensions aren't abstract math tricks but real, physical layers where spacetime behaves radically differently. In these hidden realms, constructing a wormhole might not require exotic matter or cosmic-scale engineering. It could be as straightforward as folding a sheet of paper in a dimension we've yet to discover. Consider the Kaluza-Klein model, which unites gravity and electromagnetism by introducing a fourth spatial dimension curled into a circle smaller than an atom. To us 3D beings, this extra dimension is invisible, but its influence could be profound. A wormhole in this framework wouldn't tunnel through our space, it would shortcut through the compactified higher dimension, like an ant crawling through the rolled-up center of a rug instead of trekking across its vast surface. The throat of such a wormhole might appear to us as a bizarre particle or fleeting energy fluctuation, something we'd dismiss as quantum noise unless we knew where to look. Brainworld theories take this even further, proposing our entire universe is a three-dimensional brain floating in a higher dimensional bulk. Picture a slice of bread drifting in an unseen loaf. Other brains could hover mere millimeters away in the bulk, completely invisible because light and matter stick to our brain. Here, wormholes aren't tunnels through our space but bridges between brains, their entrances appearing as sudden distortions where our local physics briefly freeze. A 4D being observing this would see the wormhole as a natural geometric fold, like watching a 2D creature puzzle over how a soda can's rim connects to its base when flattened into their plane. The real mind bender, higher dimensions might eliminate wormholes' pesky stability issues. Our 3D spacetime crushes wormholes with relentless gravity, but extra dimensions could provide structural reinforcement like adding steel beams to a cardboard tunnel. Certain string theory solutions show how quantum fluctuations in compactified dimensions could counteract collapse, making traversable wormholes not just possible, but potentially common in the higher dimensional landscape. A civilization aware of these dimensions wouldn't fight spacetime's rules, they'd sidestep them entirely, engineering shortcuts by working in directions we can't point to. Try visualizing how stepping through a higher dimensional wormhole might feel. As a 3D being, you'd experience forces tugging you in directions your body can't comprehend, like a shadow suddenly gaining depth. The wormhole's throat might appear as a shifting kaleidoscope of impossible angles, your path warping in ways that defy Euclidean geometry, and here's the kicker: when you emerged, you might not have moved far in our 3 dimensions at all. Instead, you could have hopped to a parallel brain or a pocket universe nested within our own, all because you took a detour through directions that don't exist on any earthly map. Critics argue these models are untestable, but subtle signatures might lurk in gravitational wave patterns or quantum entanglement experiments. If we ever detect particles behaving as if they briefly disappear from our spacetime only to reappear with anomalous energy, we could be glimpsing higher dimensional wormholes at work. The universe's architects may have left the blueprints for interstellar travel, not in our dimensions, but in the ones we're just beginning to imagine. Picture this: an interstellar transit system where wormholes don't just connect 2 points, but serve as bustling galactic terminals, humming with starships shuttling between civilizations. This isn't just about engineering a single tunnel, it's about weaving an entire network, a web of space-time shortcuts so vast it makes light years feel like subway stops. The energy demands alone are mind-bending. Stabilizing one wormhole might require compressing the mass energy of a gas giant into its throat. Now multiply that by thousands of nodes, each needing constant upkeep against collapse. The power sources would dwarf anything we've imagined, perhaps Dyson swarms harvesting entire stars, or black hole engines converting singularities into cosmic batteries. But energy is just the first hurdle. Building this network would demand an unprecedented level of coordination across civilizations. Who gets to map the routes? Who regulates traffic between galaxies with wildly different cultures, laws, or even biologies? A poorly placed wormhole could destabilize star systems, alter planetary orbits, or become a weapon. Imagine hijacking a wormhole's exit to flood a rival's world with radiation. The sociological implications spiral as fast as the physics. Societies linked by instant travel might homogenize, blending languages and traditions into a single galactic culture. Or they could fracture into factions fighting over control of the choke points, turning wormholes into the ultimate strategic resource. Then there's the existential question: would such a network even be desirable? Earth history shows how trade routes reshape societies, often violently. The Silk Road brought riches and plagues, the age of exploration, empires, and exploitation. A wormhole network could trigger similar upheavals on a cosmic scale, pre-contact civilizations might vanish under the weight of advanced economies, their cultures erased by the tide of interstellar commerce. Or consider the darker possibility, a predatory species using the network to expand unchecked, turning wormholes into invasion corridors, yet the potential for symbiosis is just as staggering. Shared wormhole maintenance could forge alliances stronger than any treaty. Imagine a galactic federation funded by transit tolls, pooling resources to stabilize tunnels and fund deep space research. Wormholes might even become living museums, their exits curated to preserve untouched star systems as cosmic heritage sites, their entrances adorned with art from 1,000 worlds. The network wouldn't just move ships, it could transmit ideas, blending sciences and philosophies in ways that propel entire civilizations forward. The most profound impact might be temporal. Synchronized wormhole mouths could create a universal clock, allowing societies separated by light years to experience time in lockstep. No more waiting centuries for messages. Diplomacy, trade, even friendships could unfold in real time across the void. But misalign those clocks and the network becomes a time machine, with all the paradoxes that entails. A single miscalculation could strand travelers in the wrong epoch, or worse, unravel causality itself. Perhaps the greatest lesson lies in nature's own networks. Mycelium fungi link entire forests, trading nutrients between trees in a symbiotic underground web. Wormhole hubs could mirror this, not as conquerors of distance, but as caretakers of connection, threading the galaxy into something more than the sum of its stars. The energy and cooperation required are unimaginable by today's standards, but if the universe's first wormholes were cosmic accidents, the next ones might be something far more intentional, the infrastructure of a civilization that dared to stitch the cosmos together. The universe's first wormholes might not have been forged in the fires of stars, but in the chaotic birth pangs of existence itself. Primordial black holes, hypothetical relics from the universe's earliest moments, could be hiding in plain sight as ancient wormholes in disguise. These aren't the monstrous black holes we know today, formed from collapsing stars. These would be microscopic, born from random density fluctuations in the seething plasma of the Big Bang's aftermath. And if some survive to the present, they might have undergone a bizarre metamorphosis, their crushing singularities unraveling into navigable tunnels, stitching the cosmos with shortcuts older than time itself. How does a black hole transform into a wormhole? The secret lies in quantum gravity's wild predictions. As primordial black holes evaporate over eons via Hawking radiation, their final moments defy classical physics. Instead of vanishing entirely, some theories suggest their remnants could undergo a phase transition like ice melting into water, emerging as stable wormholes. Picture a dying ember that doesn't just fade, but crystallizes into a diamond. These wormholes wouldn't require exotic matter to stay open. Their quantum structure might inherently resist collapse, preserved by the peculiar physics of the early universe. Detecting these ancient relics would be like hunting cosmic ghosts. Primordial black holes, if they exist, are already elusive, their small size making them nearly invisible. But if some converted into wormholes, they'd leave subtle fingerprints. One clue could be anomalous gravitational lensing. A primordial wormhole drifting between Earth and a distant star wouldn't just bend light like a black hole, it might create strange double or distorted images, as if spacetime itself had a kink. Telescopes like the upcoming Vera Rubin Observatory could catch these warped starlight patterns, revealing hidden knots in the fabric of reality. Even stranger signatures might lurk in the cosmic microwave background, the afterglow of the Big Bang. A primordial wormhole's gravitational field could imprint faint temperature variations or polarization swirls in this radiation, subtle scars from an object that predates the first stars. Some theorists even propose that these wormholes could act as cosmic prisms, splitting high-energy photons into unexpected frequencies, as they pass through the tunnel's quantum geometry. A gamma-ray burst that arrives with its energy signature mysteriously reshuffled might be the calling card of a wormhole older than galaxies, the most tantalizing possibility. Primordial wormholes could be clustered in halos around galaxies, drawn in by dark matter's gravity. If so, our own Milky Way might be threaded with thousands of these spacetime tunnels, some no wider than a proton. Harvesting one would be like catching smoke with your hands, but a civilization advanced enough to map their gravitational whispers could rewrite the rules of interstellar travel. Imagine tapping into a network forged in the universe's first second, a subway system written into the cosmos's DNA, yet the risks of encountering such an ancient object are as profound as the rewards. A primordial wormhole's stability would depend on physics we barely understand. Disturbing one might trigger a cascade of quantum decay, unraveling spacetime in its vicinity. Or worse, it could be a one-way door to an era before atoms formed, a portal to a universe too young and violent for life to survive. The universe's first wormholes might not just be relics. They could be frozen moments of creation itself, waiting for someone or something to wake them up. If advanced civilizations pepper the cosmos, why haven't we found a single trace of them? The Fermi paradox has haunted astronomers for decades, but wormholes might hold the answer. Imagine a galaxy crisscrossed by a hidden subway system, where interstellar travel doesn't rely on lumbering starships crossing impossible distances, but on spacetime's secret tunnels. If extraterrestrials mastered wormhole networks millennia ago, they'd have no reason to leave the visible footprints we've been searching for. No slow-moving generation ships, no telltale Dyson spheres, just a universe buzzing with activity just beyond our sight. Traditional spacefaring civilizations face brutal limitations. Even at light speed, crossing the Milky Way would take 100,000 years, an eternity for any society. Generation ships would require unimaginable resources, and cryogenic freezing or AI probes come with their own catastrophic failure risks, but wormholes rewrite the rules. A single stable tunnel could connect Earth to the galactic core in steps instead of millennia, turning the cosmos into a neighborhood. Advanced aliens wouldn't bother with visible megastructures because their infrastructure would be woven into spacetime itself, undetectable unless you knew precisely where to look. Here's the unsettling twist. Wormhole travel doesn't just make aliens hard to find, it could make us intentionally isolated. Picture a galactic community thriving in a web of interconnected tunnels, with Earth sitting in a celestial dead zone, deliberately excluded or simply overlooked. Wormholes might cluster around gravitational anomalies or exotic matter deposits, leaving regions like our sparse galactic suburb off the transit map. Or worse, what if we're the cosmic equivalent of an uncontacted tribe, preserved behind an interstellar curtain until we're deemed ready? Critics argue that even wormholes should leave forensic traces. Stabilizing them requires energies that would warp local spacetime, potentially creating gravitational lensing effects or gamma-ray signatures. Yet recent studies suggest a civilization just a few thousand years ahead of us could mask these markers using quantum vacuum engineering, cloaking their tunnels as effectively as we hide fiber optic cables underground. The universe might be threaded with wormholes, the same way Earth is laced with submarine internet cables, utterly vital, yet invisible unless you know how to dive beneath the surface. The darkest possibility, wormholes could explain the Great Filter, the hypothetical bottleneck preventing civilizations from reaching interstellar scales. Mastering spacetime might be so perilous that most species either destroy themselves attempting it or vanish into unstable tunnels. Every wormhole we theorize could be a gravestone for a civilization that dared to bend the universe's rules and lost. But there's hope in the silence. If wormholes are the universe's preferred transit system, their builders might be patient teachers, waiting for us to discover the principles ourselves rather than handing us technology we're unprepared to wield. The Fermi paradox isn't proof we're alone, just that we're still learning to see the cosmos as it truly is, not empty, but humming with hidden highways. They're on ramps just beyond the edge of our understanding. Dark energy might not just be accelerating the universe's expansion, it could be rewriting the rules of space-time itself. Holographic dark energy models take this mysterious force and fuse it with one of physics' most radical ideas, that our three-dimensional reality is a projection from a two-dimensional surface at the cosmic horizon. In this framework, wormholes aren't anomalies, they're inevitable features, woven into the universe's fabric by the interplay between dark energy's repulsive power and the holographic principle's informational constraints. At its core, holographic dark energy suggests that dark energy's density isn't arbitrary but tied to the universe's horizon size, the maximum distance light could have traveled since the Big Bang. This creates a cosmic feedback loop where expansion alters dark energy, which then drives further expansion. But here's the twist: if the universe is fundamentally holographic, with all 3D information encoded on a 2D boundary, then dark energy's behavior might also encode spacetime's architecture. Wormholes in this model emerge as defects in the projection, like glitches in a cosmic hologram where the data gets folded back on itself. Imagine spacetime as a vast, shimmering hologram projected from the edge of the observable universe. Most of the time, the projection runs smoothly, creating the illusion of seamless three-dimensional space. But where dark energy's repulsive force interacts with quantum fluctuations in the holographic data, tiny wormholes could pop into existence not as physical tunnels, but as quantum entanglements in the underlying code. These wouldn't require exotic matter to stabilize; their existence would be baked into the universe's operating system, like shortcuts in a computer program that bypass normal processing steps. The math behind this is as elegant as it is strange. Holographic dark energy models predict that the universe's total information content is finite and proportional to its horizon area. Wormholes in this context act as quantum error correcting codes, ensuring information isn't lost when spacetime stretches. Picture a cosmic hard drive where wormholes are the redundancy checks, preserving data integrity across cosmic distances. This could solve long-standing puzzles like the black hole information paradox, while simultaneously explaining how traversable wormholes might persist without violating energy conditions. Critics argue that holographic wormholes are untestable abstractions, beautiful math without observable consequences, but subtle signatures might lurk in the cosmic microwave background's polarization patterns or in anomalies in large-scale structure formation. If holographic dark energy is real, wormholes could imprint faint statistical irregularities in the distribution of galaxies, like shadows cast by invisible threads stitching the cosmos together. Future telescopes mapping the universe in unprecedented detail might spot these telltale wrinkles, revealing a reality far more interconnected than we ever imagined. The boldest implication: if holographic dark energy permits wormholes, then mastering them might not require bending spacetime, but reprogramming it. Advanced civilizations could treat the universe like a vast quantum computer, manipulating the holographic data at its boundary to spawn wormholes on demand. The cosmic shortcuts we've been searching for might not be out there in the stars, but embedded in the very code of reality, waiting for us to learn the syntax. Unlocking this wouldn't just revolutionize travel, it would prove we're living in a universe where information is the ultimate currency, and wormholes are its most fascinating transactions. Einstein's equations have reigned supreme for over a century, but what if they're just the first draft of gravity's true story? Quantum gravity corrections, the tweaks needed to bridge general relativity with the quantum realm, might hold the key to wormholes far stranger than Einstein ever imagined. These adjustments aren't minor footnotes; they could rewrite the rules entirely, bending spacetime in ways that make wormholes not just possible, but inevitable, no exotic matter required. Picture this at the tiniest scales where space-time fractures into a seething quantum foam, gravity's behavior flips. Here, the smooth geometry of relativity gives way to wild fluctuations, with probabilities replacing certainties. Some quantum gravity models predict that these microscopic disturbances don't just cancel out, they accumulate, twisting spacetime into structures that defy classical physics. Wormholes in this regime wouldn't be cosmic anomalies, they'd be as natural as quantum particles popping in and out of existence. The catch, their stability hinges on corrections to Einstein's equations that kick in only under extreme conditions like those in the early universe or near black hole singularities. Take loop quantum gravity's approach. Unlike relativity's smooth continuum, spacetime here is woven from discrete, indivisible loops. When these loops knot together under quantum corrections, they can form self-reinforcing structures that resist collapse, no exotic matter needed. It's like comparing a sandcastle to a 3D printed lattice. One crumbles under its own weight, while the other's intricate design distributes forces to stay intact. Simulations show these quantum-corrected wormholes could remain open long enough to traverse, their throats propped up by the raw energy of spacetime's granularity rather than hypothetical negative energy. String theory offers another twist. In some higher dimensional models, quantum corrections introduce extra terms to Einstein's equations that counteract gravitational collapse. Imagine spacetime as a trampoline. Normally, a heavy weight creates a steep dip that pulls everything inward, but quantum corrections might act like hidden springs beneath the fabric, pushing back to create a stable tunnel. These adjustments could emerge naturally from Calabi-Yau manifolds vibrating in extra dimensions, their geometry subtly altering how gravity behaves on macroscopic scales. The implications are staggering. If quantum gravity makes wormholes viable without exotic matter, they might not be rare cosmic oddities but ubiquitous features, woven into the universe's fabric at birth. The first wormholes could have formed in the Planck epoch, moments after the Big Bang, when spacetime was still malleable enough for quantum fluctuations to pinch it into tunnels. Some might still linger today, frozen relics waiting for the right conditions to reactivate. Others could flicker in and out at the quantum scale, stitching together distant points in an ever-changing web. Critics argue these corrections are too subtle to matter outside black holes or the early universe, yet recent breakthroughs in analog gravity experiments where quantum fluids simulate spacetime dynamics hint that quantum corrections might have macroscopic effects. Lab-created wormholes in Bose-Einstein condensates have already demonstrated how quantum pressure can stabilize spacetime shortcuts, mimicking predictions from full quantum gravity theories. If these phenomena scale up, nature might have already built the universe's transit system. We just need to learn its quantum syntax. The boldest take. Quantum gravity could turn wormholes from sci-fi dreams into engineering projects. Master these corrections, and you're not just exploiting spacetime, you're collaborating with it, coaxing the universe to reveal shortcuts it's hidden since creation. The first travelers might not break physics to open wormholes, they'll simply ask the quantum world to show them the doors already there. Quantum entanglement already feels like magic, particles influencing each other instantly across any distance. But what if wormholes transform that spooky connection into something even more revolutionary? Imagine quantum computers not limited by lab walls, but linked through spacetime tunnels, processing data at speeds that defy physics as we know it. This isn't just about faster calculations, it's about redefining the very nature of information. The key lies in the ER=EPR conjecture, where entangled particles are secretly connected by microscopic wormholes. Scale this up and you've got a quantum network where bits don't just teleport through empty space, they shuttle through space-time shortcuts. A qubit enters a wormhole on Earth and emerges light years away, its state perfectly preserved, bypassing the delays of conventional signaling. No more latency, No signal degradation, just instantaneous communication anchored by the universe's own geometry. Lab experiments are already nudging this from theory toward reality. In 2022, researchers at Caltech simulated a holographic wormhole using Google's Sycamore quantum processor. By entangling qubits in specific configurations, they replicated the gravitational dynamics of a traversable wormhole, effectively creating a quantum-scale model of space-time tunneling. The simulation didn't just mimic wormhole behavior, it suggested that quantum systems might inherently encode space-time structures we've yet to decode. Here's where it gets transformative. Traditional quantum networks face a bottleneck. Entanglement distribution slows exponentially with distance due to photon loss in fiber optics. Wormhole link systems could leapfrog this entirely. Picture a quantum internet where every node connects through stabilized space-time bridges, making distance irrelevant. Sudden breakthroughs in cryptography, materials science, or AI wouldn't unfold over decades. They'd cascade globally in real time, as if every researcher shared the same lab bench across continents. But the risks are as profound as the rewards. A wormhole quantum hybrid might expose space-time to unprecedented vulnerabilities. Manipulating entangled particles through a tunnel could destabilize the wormhole structure, creating feedback loops that shred quantum coherence or even collapse the passage. And then there's the existential question: if information traverses a wormhole, does it retain its quantum nature or emerge altered by the journey? One miscalculation could scramble data into cosmic noise. The most tantalizing possibility: wormhole computing might not stop at earthly networks. If quantum signals can traverse space-time tunnels, could they reach quantum processors orbiting other stars, or in other epochs? A civilization harnessing this wouldn't just break computational barriers, they'd weave space-time itself into their machines, turning the universe into the ultimate operating system. The first functional wormhole quantum link wouldn't just revolutionize technology, it would prove that information, like gravity, can bend the rules of reality. What if our universe didn't begin with a bang, but with a bridge? The boldest twist in cosmic origins suggests the Big Bang wasn't an isolated explosion, but the violent reopening of a wormhole linking our newborn reality to something far older. Imagine a parent universe, ancient and vast, where the gravitational collapse of a dying black hole didn't end in oblivion, but in rebirth, its singularity stretching into a tunnel that birthed our cosmos like a seed sprouting through space-time soil. This radical vision springs from cyclic cosmology, where universes don't live and die in isolation, but are nodes in an infinite chain of cosmic reincarnation. Each cycle begins when a collapsing universe's contraction reaches critical density, triggering not a crunch but a bounce, a rebound so fierce it warps the fabric of reality into a wormhole, spewing its energy into the next cycle's Big Bang. The equations behind this are breathtaking. Under extreme conditions, quantum gravity corrections could twist a black hole's singularity inside out, transforming it into a white hole erupting with new spacetime. Our entire universe might be the other side of some grandparent cosmos's catastrophic collapse, its laws of physics imprinted by the way reality tore and reformed in the transition. Evidence for this audacious idea might be written in the sky. The cosmic microwave background, the afterglow of the Big Bang could bear scars from the wormhole's throat. Some models predict subtle temperature variations in this primordial light, spiral patterns echoing the torsion of spacetime as it twisted into a tunnel. Others suggest the universe's startling uniformity, the way distant regions have identical temperatures despite never being in contact isn't from inflation smoothing things out, but because they were once connected through the wormhole's bottleneck, sharing conditions before the Great Rupture. But the most mind-bending implication: if the Big Bang was a wormhole, there might be other sibling universes branching from the same cosmic umbilical cord. Our cosmos wouldn't be unique, but one of many buds on an infinite tree of spacetime. each with subtly different physical constants depending on how their birthing wormhole stabilized. Some could harbor matter that behaves in ways we'd call magic, others might be stillborn, collapsing instantly under incompatible physics, and if the cycle continues, our own fate might be to collapse into the next universe's wormhole, a cosmic Ouroboros eating its own tail for eternity. Critics argue this pushes speculation beyond science. How could we ever observe a parent universe? Yet mathematics offers tantalizing support. Certain solutions to quantum gravity equations naturally describe wormhole-to-bang transitions, with no need for ad hoc inflation fields. And if dark energy's acceleration leads not to eternal expansion, but to a future Big Rip, the shredding of spacetime itself might birth the next cycle's wormhole in the wreckage. The universe's death could be another's genesis, creation and destruction locked in an endless dance. Perhaps the most haunting question isn't whether this happened, but what passed through the wormhole before us. If our universe inherited its structure from a predecessor, traces of that ancestry might linger in quantum anomalies or shadow particles resisting all detection. The first travelers through the cosmic tunnel weren't astronauts or aliens, but the raw laws of physics themselves, carrying the blueprint for everything we know. Wormholes wouldn't just connect space, they'd stitch time, causality, and existence into a tapestry more interconnected than we ever dared dream. From the cosmic blueprints hidden in Einstein's equations to the quantum foam's fleeting shortcuts, from the holographic universe's data bridges to the multiverse's tangled gateways, we've journeyed through 30 electrifying theories about the universe's first wormhole travelers. Each idea is a testament to human ingenuity, a daring attempt to crack the code of spacetime itself. Some are grounded in rigorous math, others flirt with the fringes of speculation, but all share one thing: they remind us that the cosmos is far stranger than we ever imagined. The fact that wormholes can emerge from black holes, quantum entanglement, dark energy, or even the Big Bang's echoes proves there's no single path to unlocking these cosmic tunnels. Physics isn't a closed book, it's a living puzzle, and wormholes might be its most tantalizing piece. What's astonishing isn't just the variety of theories, it's how many could be simultaneously true. Wormholes might arise from multiple mechanisms, each leaving its own signature in the fabric of reality. Perhaps primordial black holes birthed the first tunnels, while advanced civilizations engineered others. Maybe quantum foam spawns ephemeral shortcuts even as dark energy weaves grand celestial highways. The universe doesn't do simplicity, it thrives on layers, and wormholes could be its ultimate hidden architecture. Yet for all our theorizing, the biggest questions remain unanswered. Are wormholes naturally occurring, or always artificial? Do they inevitably lead to time paradoxes, or does the universe enforce cosmic censorship to prevent chaos? And most haunting of all, if wormholes exist, why haven't we found one yet? The silence could mean we're not looking right, or it could hint at something profound, that traversable wormholes require technologies or understandings still beyond our grasp. Here's where you come in. Which of these theories resonates with you? Do you see wormholes as nature's handiwork, or the artifacts of ancient starfarers? Could they be lurking in plain sight, disguised as black holes or quantum quirks? Or are we missing a radical possibility no one's even proposed? The conversation doesn't end here. Drop your favorite theory in the comments, and let's keep the debate alive. If this deep dive left you hungry for more cosmic mysteries, you're in luck. From white holes to time loops, from dark matter's secrets to the holographic principles' implications, our channel is your portal to the universe's greatest enigmas. Hit subscribe and together we'll keep unraveling the cosmos, one mind-bending theory at a time. The universe has been keeping its secrets for billions of years, but the age of discovery is just beginning.